In this video, we're going to be looking at applying Newton's first two laws to systems. So we're going to be specifically looking at coupled motion. So a coupled motion is where objects are attached by a rope. There are many interesting situations we could study, but for this course, we're just going to look at two major scenarios. The first one is the Atwood machine, and the second one is the lab situation that you guys just did the last class. So let's first take a look at how we solve things with this Atwood machine, where we have two masses that are in the balance, and one will obviously go up and one goes down if the masses are different. So let's take a look at our first example of an Atwood machine. In an Atwood machine, we have two masses suspended by a pulley. If the masses were equal, we would assume that neither of them would accelerate because the forces would be equal. In this case, though, we know that mass 2 is greater than mass 1. Therefore, by logic, we could assume that mass 2 would have a greater force, and mass 2 would go down, accelerate downwards, and mass 1 would accelerate upwards. So let's try and draw a free body diagram of this. Now, the force pulling mass 1 up is called the tension in the rope. Tension is just the same as force is equal to ma. So my tension is going to be my upward force, and my weight, or the force of gravity, is going to be my downward force. For mass 2, the tension again is the upward force, and my force of gravity is my downward force. The difference between mass 1 and mass 2, though, is in mass 1, my tension is going to be greater than the force of gravity, and in mass 2, my tension is going to be less than the force of gravity. So what exactly is tension? Well, tension is when an object is being pulled by a rope, the rope exerts a force on the object. That force that is exerted by the rope is called tension. So now that we know what tension is, let's go back to our previous question here and add some values to our masses. So in our question, we're going to suppose that mass 1 has a value of 25 kilograms and mass 2 has a value of 35 kilograms. We want to first calculate the acceleration of the system, and then B, find the tension in the rope, which is, once again, just the force in the rope. So I'm going to break this down into two parts. We're going to look at mass 1, which goes up, and then a second part, which is mass 2, that goes down. So for mass 1, which moves up, we know the applied force, or the net force on that mass 1, is going to be equal to the tension minus my weight, or my force of gravity. In other words, we know that the mass 1 multiplied by its acceleration is going to be equal to my tension in the rope, subtract the mass of mass 1 multiplied by gravity. We're going to plug in what we know, so I know 25 kilograms is equal to my mass times acceleration is equal to my tension minus 25 kilograms multiplied by 9.81 meters per second. We end up getting a total of 25 times my acceleration is equal to my tension minus 245 newtons. Now I'm going to look at my other side where we have mass 2, which is going down. In this case, my F net for mass 2 is going to have my weight of mass 2 is going to be greater than my tension. So I'm going to write it as F net is equal to my force of gravity minus my tension. In other words, we have my mass times acceleration, or my F net, is equal to my mass times gravity, subtract the tension. So here we have a mass of 35 kilograms multiplied by acceleration is equal to 35 kilograms multiplied by 9.81 meters per second squared. Then we're going to subtract my tension. So we end up getting 35 multiplied by acceleration is equal to 343 minus my tension. On my other side here for mass 1, I am going to solve or isolate my tension. So I'm going to have 25 multiplied by acceleration plus 245 is equal to tension. Now what I'm going to do is I am going to put in, for my tension in mass 2, the value of tension using system of equations substitution. So now I end up getting 35 times acceleration is equal to 343 minus 25 multiplied by acceleration plus 245. we end up getting 35 is equal to 343 minus 35a minus 245. This gives us, putting all my a values on one side, my variables on one side, 60a is equal to 98, which gives me an acceleration of 1.63 meters per second squared. Now to find my tension, all I have to do is put my acceleration back into one of my equations above here, and I'll be able to find my tension. So if I put 1.63 in for 25 times acceleration plus 245 is equal to tension, I'm going to end up getting a tension of 285.7 newtons. In our second Atwood machine example, we are not given the masses here, but we are given that mass 1 is 3 times that of mass 2. So to help us out here, first we're going to draw a free body diagram. Since mass 1 is more, I know my force of gravity is going to be bigger than my tension. For mass 2, I know my tension is actually going to be bigger than my force of gravity. For both of these, just like the last one, I know my tensions should be equal. So what may be complicated here is we're looking at this. There's 3 variables that we don't know. Well, actually 4. We don't know either mass, we don't know the tension, and we don't know the acceleration. But that's okay. We can still use a system of equations because in this situation, my masses interfere with each other, so they're proportional. As long as we know the proportion, we can still solve this the same way. So in this case here, my down, remember, is m1. So I'm going to start with my downside, which is mass 1. We're going to look at the mass 1 system to start off with. So here we know the force of mass 1 is equal to the force of gravity of mass 1 minus the tension. So my net force of mass 1 is my mass times my acceleration, which is equal to my mass 1 multiplied by gravity, subtract my tension. Now I also know that mass 1 is 3 times that of mass 2. So therefore I could give mass 1 a value of 3 and mass 2 a value of 1. So in this case here I'm going to say 3 times acceleration is equal to 3 times 9.81 minus my tension. So now let's look at my second half, mass 2. In this case, mass 2 is going to be going up. So for this one, we're going to say the net force of mass 2 is equal to tension minus the force of gravity for mass 2, because it's moving up, so tension must be bigger, according to our free body diagram. So once again, we have mass 2 times acceleration is equal to tension minus mass 2 multiplied by gravity. This ends up giving me my acceleration is equal to tension minus 9.81. In other words, we have tension is equal to acceleration plus 9.81. Now that I know this, I could use a system of equations to combine these equations and eliminate tension so I could solve for my acceleration. So I'm going to end up getting 3a is equal to 3 times 9.81 minus acceleration plus 9.81. I'm going to end up getting 4 times acceleration is equal to 2 times 9.81. Acceleration is equal to half of 9.81, which is equal to 4.905 meters per second squared. Now to solve this, all I have to do is put my answer for acceleration into one of my equations up here for mass 2 or mass 1 to solve for tension. I would put it in for mass 2. So now let's look at our lab situation scenario. In this case here, we have a mass being pulled across the table with another mass going down. We're going to look at 2 scenarios. The first one will be with no friction, and the second one will be with friction. So to start this off, the first thing we want to do is make a free body diagram for each mass, mass 1 and mass 2, because we have, once again, 2 situations. We have a situation for mass 1, and we have a situation for mass 2. So my free body diagram for mass 1 is going to be, we have my normal force going up, which is going to be equivalent to my force of gravity going down, and then we have my tension in the x-axis. My free body diagram for mass 2 is going to have tension going up and my force of gravity going down, which is going to be bigger, most likely, than my tension. So once again, just like our Atwood system, we are looking here for the acceleration. And we're going to separate them into mass 1 scenario and mass 2 scenario. So my force for mass 1 is going to be equal to tension, and because my tension is my only real force, net force here. So in this case, I have mass 1 times acceleration is equal to tension. So I'm going to get 20 times acceleration is equal to tension. Now we're going to look at mass 2. Here, my net is going to be in the y. In this case, we're going to have my force of gravity minus tension is equal to my net force. So here I get mass 2 times acceleration is equal to mass 2 multiplied by gravity minus tension. Altogether, I'm going to get 5 multiplied by acceleration is equal to 5 times 9.81 minus tension. So now I'm going to get 5a is equal to 49.05 minus tension. And I could put in the 20a in for tension. So once again, we have now, after substitution, 5a minus 49.05 minus 20a. We end up getting 25a is equal to 49.05. A, my acceleration, is equal to 1.96 meters per second squared. So now to calculate tension, all I'm going to do is put my acceleration into one of my formulas for my masses. And I'm going to use the mass 1 formula because it's a little bit simpler. So I'm going to go tension is equal to 20 times acceleration. So tension is equal to 20 times 1.96. Therefore, tension is equal to 39.24 newtons. Now my second example that's given the lab situation has friction, but it's really not that much more difficult. So we're going to start off the same way again, and we're going to draw a free body diagram for each one. So if I look at the free body diagram for mass 1, we know my normal force is going to be equal to my force of gravity. Then we have our tension in a rope going to the right, and my force of friction going left. Now let's look at the free body diagram for mass 2. In this case, we have the tension going up and my force of gravity going down. So to find the acceleration, we're going to separate it once again into our calculations for mass 1 and our calculations for mass 2. This one here is going to be a more similar setup of what it looked like in the Atwood machine. So here we're going to start off with mass 1. We're going to know my net force for mass 1 is equal to tension minus my force of friction. In this case, we get mass 1 multiplied by acceleration is equal to tension minus my force of friction. In this case, I'm going to get 30 times acceleration is equal to tension minus 20. Now let's take a look at mass 2. Here we know the net force for mass 2 is equal to the force of gravity minus tension. The mass 2 multiplied by acceleration is equal to mass 2 multiplied by gravity minus tension. We end up getting 10 times my acceleration is equal to 10 multiplied by 9.81 minus tension. So we end up getting 10 times acceleration is equal to 98.1 minus tension. So I'm going to isolate for tension on my mass 1 side. So I'm going to end up getting 30a plus 20 is equal to tension. Now I'm going to substitute that in to my other side. So for mass 2. So I end up getting 10 multiplied by acceleration is equal to 98.1 minus, all in brackets, 30 multiplied by acceleration plus 20. So I end up getting 10 multiplied by acceleration is equal to 98.1 minus 30 multiplied by acceleration minus 20. So I end up getting 40 times acceleration is equal to 78.1. My acceleration ends up being 1.95 meters per second squared. Now to find my tension, all I have to do is put 1.95 meters per second squared into this formula here to give me my tension.